Just flipping
And adding one.
All right, how's it going? So, any questions up to here?
Is the one before the I do have a question. On the homework assignment, so on number 2, we have to convert sine to decimal.
Okay.
We learned that using the 4-bit method, how like do the complement. Could you do the exact same thing on the 8 bits?
Yeah.
The complements, you add 1. Yeah. And that's
Yeah, however many bits you have, you complement the whole number every bit, add 1, that gives you the negative.
And even if it's a positive.
If it's a positive, that'll give you the negative. If it's a negative, that'll give you the positive.
Because one of the examples, it was like, say, the bit was 107, the decimal was 107. You do the complement, you add 1, you add it up together, it becomes 21.
So what was it in binary?
The binary was 0, 1, 1, 0, 1, 0, 1, 1.
Okay. So you take the 2's complement, right? So complement. So what is this number, first of all, in
It's
decimal?
107.
It's 107. Okay, so complement all the bits,
Add 1.
add 1. That should be negative 107. And if you add this number with this number, you should get 0. So 0, 1, 1, 0, 1, 0, 1, 1, plus 1, 0, 0, 1, 0, 1, 0, 1. So that'll give you 0 with a carry, that's 0 with a carry, and so on. There's your 0.
I guess that's how you got negative 107 from that. You just know what's the negative root from 107?
I got negative 107 because this was positive 107, and then I complemented it and added 1. That makes this the representation for negative 107.
But if that number was just standing there by itself, there's no way you could have told that was negative 107, right?
Not unless you did some work.
Okay.
So what's the work you have to do? Well, if you're given this number, so let's say this. So working in 8-bit, 2's complement. And this is important. We need to know we're dealing with 8-bit numbers, and we need to know we're working with 2's complement. Okay, so working in 8-bit 2's complement, what is 10010101 in decimal? That's a classic exam question. Well, you have to do a couple of things. The first thing you have to do is look at this most significant bit, right? So most significant bit's on the left, least significant is on the right. So this is most significant bit. And if it's a 1, this is a negative number. That's one of the features of writing things in 2's complement. If that most significant bit is a 1, then this is a negative number. If it's a negative number, we don't want to just start adding up powers of 2. That really only works with positive numbers. So let's find the negative of this. So find the negative of this number.
This is for sine, yeah?
This is all for sine, yeah. Yeah, 2's complement means that it's sine, basically. So how do we find the negative value of this 8-bit 2's complement number? First, we complement all the bits, and then we add 1. And now we have an extra step, convert to decimal by adding powers of 2. So this is 2 to the 0 plus 2 to the 1 plus 2 to the 3 plus 2 to the 5 plus 2 to the 6 and I'm trusting you when you tell me that equals 107. And therefore, 3 dots mean therefore. This original number is negative 107.
So I'm sorry, I'm still confused. So there's a 1 at the beginning, and it's signed, that means it's a negative number.
Mm-hmm.
100% of the time?
Say again?
100% of the time?
100% all the time. If it's 2's bit, 2's complement, and that first digit is a 1, it is a negative number. It's less than 0.
So the reason I'm confused is that, let's take for example the first one and number 2, the same number, it starts with 0. And
Mm-hmm.
then you 2's complement it, and then it has a 1.
Yes.
So why is that negative if it started at the 0, not a 1?
If it started with a 0, it was a positive number.
But you just said it was negative. You said we got 107, and then, so we had to start with a 0, we complemented it, it started with a 1. Then you said, and that ended up being 107, then you added a negative. Before this, it was the last day.
So this one?
Yeah, so it starts
So
with
this is
0,
positive 107.
And then you complement it, and it.
We complement and add 1, that's going to give us negative 107, and there's a 1 in that most significant bit.
Okay.
Okay, do you agree that this 8-bit number that starts with a 0 is positive 107?
Yes.
Okay, so our goal is to find an 8-bit number that corresponds to negative 107.
Wouldn't the answer, if you're converting that number, the original, not the 2 complement, to signed decimal, wouldn't the answer just be 107 then?
Say it again?
If it just says to convert to signed decimal, and the original number in binary starts with a 0, not a 1, then wouldn't the answer be positive?
Yes. If it starts with a 0 and we convert to signed decimal, it's going to be a positive number that we get.
But you just got it, okay.
And I converted this number and I got 107,
Okay,
right? So this number corresponds to 107.
so for the first part of question 2, you didn't need to use complement at all?
Nope.
Okay.
Yeah.
That was the confusion. So you only.
No, so in the first part, right, so it says convert this to signed decimal, your answer here is positive 127,
One.
or positive 107.
Okay.
Yeah,
And then the other 2 you choose complement, and that gives you the negative version.
right. You got a question?
Yeah, I got it.
You got it? Okay, yeah.
I have a question now. So when you say convert to an unsigned decimal, then do we just assume it's positive? And then if we say convert to a signed decimal, then if it's a positive number, do you want us to change it to a negative number?
No, if we say convert to signed decimal, and I could have phrased this differently, I could have said using 2's complement notation, right? Convert to a signed decimal. So signed does not mean it's positive, it does not mean it's negative. It means it could be either. It means we're using a representation that can be used for both positive and negative numbers,
Okay, so.
i.e. 2's complement.
So then that one with 107, that's 107 for both the first one and the second one, right?
So convert to unsigned decimal, that's 107. Convert to signed decimal, that's also 107,
Okay.
correct? Right? Convert to unsigned decimal, this number is 255, right? You add up all those powers of 2. But if we convert to signed decimal, this middle number is actually, what did you find? Negative 1, right? So all that's really going on here is that we have 2 ways that we can interpret a string of 1s and 0s as a number, right? One way is just to add up all the powers of 2. And we know we're going to get something between 0 and some large positive number, right? And there's no way we can get a negative number if we're just adding powers of 2, right? It's always going to be 0 or bigger. So that's an unsigned conversion. But if we want to be able to represent negative numbers, we use this 2's complement notation, and we can't just add powers of 2, because if we added powers of 2, we'd add an extra 128 over here at the end, and everything would go wonky, right? So we use this complement and add 1, that's how we choose to represent. Now, that's not the only way we could represent negative numbers, right? We could do what we do as humans. So here's the number 45,763. If we want the number negative 45,763, how do we write it? Yeah, we put a little mark in the front here. We don't complement and add one or do something goofy like that. We just add an extra thing in the front. And another way to look at that is if we want a positive version, we write a plus sign in the front, but we usually suppress it. If we want a negative version, we put a negative sign in the front. So we have an extra character in the front that we use to say whether the rest of this is positive or negative. If it's negative, we put a minus. If it's positive, we put a plus, or maybe we just leave it blank. So that's something called signed magnitude. So signed magnitude notation has nothing to do with 2's complement. So in signed magnitude, that's the number 107. We might write negative 107 by just changing that first bit to a 1. Right, so this means bigger than or equal to 0. This means less than 0. But that's not 2's complement. Okay, this is not the number that we found when we calculated the 2's complement and found negative 107. Different pattern of bits. So if you're a computer and you see this 8-bit number and you're asked to add something to that, you got to know, what is this number? Is this negative 107 because the person used sign magnitude, or is it the 2's complement of some number, or is it just an 8-bit unsigned number that's bigger than 128, 200 something, right? So we have these different notations that we can use. Most of what we do in here, we're going to use 2's complement. Most of what you'll do in Engineering 270 and in computer science classes is based on 2's complement. But there are other ways that we can do this, including this very kind of human-centric idea.
Just out of curiosity, this one, since I guess it wouldn't have the negative 128, what would that be?
If you use sign magnitude, you can go from positive 127 to negative 127.
So what would 1,0,0,0,0,0,0,0?
Technically, it would be minus 0,
Okay, just curious.
which would be 0. And that's an interesting question. When we talk about floating point, we'll see that there's different ways you can represent 0, different bit patterns. And typically, you might use these other representations to mean something else. Like if we wanted the ability to store something that's not a real number, we might say, okay, that's a 1 followed by 7 zeros. And now if you, I don't know, divide by 0, maybe we put that as the answer. And when you look at it, you say, oh, that's not a real number, something went wrong. So negative 128 was the oddball in that question too. Because if I said convert this to a signed decimal, right? Well, you look at this, and I just told you that I guarantee that's a negative number. So you want to take the 2's complement. So complement. And you get this. And that's where we started. That's a little weird. So this is the one number that's a little bit strange. You have to kind of like forget what you're doing for a moment and say this is 128, and therefore this is negative 128. But that's a little discomforting. So treat this as a special case. It's definitely negative, but this is negative 128. It's an oddball because technically we can't write positive 128 in 2's complement with only 8 bits. Right, we can go from negative 128 all the way to positive 127.
Could you view it as if it's signed, if you classify as signed, then if it's a negative, like we talked about the first
bit.
Couldn't you say like we're still doing by 2's, like 2 to the power of? The last one could be 2 to the power of 7, but negative, so negative 128.
Yeah.
That's the way that I did it, is I started off, the first one is a negative,
Then you add it
is the
up.
one that, 120, negative 128, and then I add the other bits, and it still ended up being negative 1.
So you're subtracting 128 from what you get?
Or add, yeah.
Okay, yeah. That works equally well, because really all we're doing is right, we're scaling these things. Instead of 0 to 255, we're going negative 128 to 127. So yeah, that's a good way to do it too. All right, let me mention one thing that sometimes trips people up. If, maybe we already had it on here. Yeah, so this did come up. So if I say convert this number using 2's complement to a signed decimal, it doesn't mean it's going to come out negative, right? 2's complement does not mean negative. And sometimes I'll say, express this number in 2's complement, and people feel like they have to throw a minus sign in the front because it's 2's complement. That's not the case, okay? 2's complement is just saying we can have positive or negative numbers, but if they're negative, we use this algorithm to write down the bit pattern. Okay, but a positive number can be written in 2's complement, and it's a positive number. All right, any problem converting to hex into octal? All right, so is everybody comfortable with their solutions on their homework? Okay, go ahead and pass those in then. That makes my grading really easy. There's the staker in the front desk area, but just fold it over for now.
I've done more for it. I'm just,
Okay. All right, got everybody's homework?
Has to rewrite my.
Okay. All right, how's lab 1 coming? Good? So that YouTube video is just a channel called ENGRCS, right? Same as the website. And you sometimes have to scroll down to the bottom and either say load more or wait for it to load more. But if you search for the word scope and keep getting it to load more, right, it'll bring you to a video that talks about these things. So there's a 13-minute video on the oscilloscope. So these are courtesy of Izad. So any questions about the equipment so far?
On the lab, it asks us to sketch out like whatever we get. Is it all right if we just take a picture?
I'd rather you sketch it, and you don't have to make it like precise or beautiful. I get some works of art once in a while, which is always awesome, but it kind of forces you to sort of engage a little more with the controls and stuff. So it can just be a really crude drawing with a few circles for the knobs you want to describe and such. But yeah, go ahead and sketch it out by hand. And for labs, right, sketches and things like that, you can draw by hand. If you really like doing these things on a computer, go for it. But don't spend time trying to, go into Paint or whatever your favorite tool is to make pictures on the computer, right? Just draw them neatly by hand. Get a piece of graph paper if you're drawing circuit diagrams or something and you want to keep things parallel. But draw those things by hand and include them in your lab report. And if you're not sure how to do that, right, this is a good opportunity to figure that out. Because everything you do in school and everything you do on the job after school and so on, you're going to be producing paper, right? I mean, it'll be electronic usually, but you're going to be producing reports and you're going to be including things in. And you can use your time here at Clark to continue developing a toolkit, your own personal toolkit of things that you use to do things like produce reports. So for example, in Windows, there's something called the snipping tool that you can use to grab a part of your screen, and then you can crop it and scale it and lighten it and darken it and so on. There's a freely available tool called IrfanView. That used to be my favorite tool under Windows. Same thing, you can take a screenshot, you can crop it, you can rotate it and so on. And all of these things, you can save the result as a PNG or a JPEG or whatever, and then drag that into a document. And it's good to sort of develop a toolkit, like I say, for doing these things. If you have a phone with a camera and you have good lighting, you can take a picture of something on a piece of paper. But spend some time trying to figure out how to get good quality like that. All right, bless you. Most of us don't have scanners or access to scanners anymore. They've kind of gone by the wayside. But cameras will do a good job. But if you draw a circuit diagram, you take a picture with your phone and you email it to yourself and then try to put it in your report, make sure it's very legible, okay? If you've got all this little detail written in there and it just looks like a blur, right? Spend some time and try to refine that. Talk to your friends, talk to classmates and say, how did you include your circuit diagram? And learn some new tricks, right? Or share some tricks with others.
Does it have to be like actually scanned in, or can you just have it on a paper just with the rest of the lab report being in?
So you're turning these things in electronically,
Oh,
right? So you want to scan it.
yeah, just scan it.
Yeah. All right, so let's see. We're going to talk more about experiment 6. We'll talk about truth tables and system diagrams and stuff for the rest of this. So any other questions? Yes?
Not really a question, but if there's anybody else who hasn't got a lab partner yet, then maybe they come and chat with me afterwards, otherwise I'll find somebody that, not on the group.
Cool. Anybody else still missing lab partners? Okay. Cool. All right. Talk. And I think I already mentioned this before, but just in case I didn't, my official lab hours are Fridays from 12 to 3. Right? You can work in the lab any time that you want that the lab's open. You don't have to be there when I'm there. But if you want to be guaranteed to be able to find me in the lab, Fridays 12 to 3 is a good time. But I also have office hours most days, and you can always catch me during office hours. And I'm right next to the collaboratorium, so you can find me and say, hey, can you take a look at my circuit or whatever. That's always an option. How many people here are familiar with the Engineering Computer Science Club? How many people like free pizza? All right. So the ECS Club meets every Friday, 12 o'clock, and it's in this building, and it's room 126. And they're supposed to have free pizza most meetings, hopefully including this week. So what's the ECS Club? It's a bunch of students who have some degree of interest in engineering, computer science, aerospace, whatever, and they get together every Friday at noon. And it's an official ASCC club, so there might be a few minutes of club business, especially in the beginning of the quarter, where they, vote for new officers or talk about money, thanks, or whatever. And then it's really just kind of up to whatever the students want to do. So typical things we've done in the past, the club will arrange field trips. So they've gone to visit the nuclear reactor at Reed. They've taken trips to Bonneville Dam. They've taken trips to area companies. Like you want to go see Intel, some part of them, and somebody knows someone who works at Intel, and they might arrange to get a tour of some facility. And so everyone piles into some vans and they drive out to Intel, right? We have speakers come in sometimes and give talks. So there's activities like that. And it's also a chance for students to interact with one another and say, hey, you know, I've got a drone that can be programmed and I'm really trying to write some code for it, but I don't have a really good understanding of Java. But I'm really good with the engineering side of it. If there's anybody who knows Java and wants to work with me on this, let me know, right? And so there's that kind of networking going on. And it's really just an informal get-together. It's a chance to hang out with fellow engineers and do some brainstorming and swap ideas and stuff like that. There's no commitment, there's no obligation, there's no sign-up, there's no cost. It's really just show up and hang out and leave when you want. But you can also get free food sometimes. So that's every Friday starting tomorrow, 12 o'clock, SBG 126. So take advantage of that if you like. It's usually a pretty good setup. All right, so let's talk a little more about binary numbers. One thing we didn't talk about last time is how to convert from decimal to binary. And the other direction is more straightforward. Just add up powers of 2, or maybe do this funny 2's complement thing if you've got a negative number. But going from decimal to binary takes a little more work, right? So for example, we have the number like 43, and we're asked to write that as a bunch of 1s and 0s. So we do this in 120, and depending on which class you take, there's different techniques for doing this. One approach is sort of trial and error, right? So 64 is too big, but 32 fits into here, so we'll put a 1 down for 32, and we'll subtract that, and then 16 is too big for the remainder, and so on, right? So let me show you a technique for converting from decimal to binary. And this is only for positive numbers. Okay, so if it's negative, we're going to want to convert the positive value first and then take a 2's complement. But if you have a number like 43 and you want to convert to decimal, here's a way to do this. So write your number down, divide it by 2. So 43 divided by 2, that's 21 with a remainder of 1. Okay, now repeat. 21 divided by 2 is 10 with a remainder of 1. Repeat. 10 divided by 2 is 5 with a remainder of 0. 5 divided by 2 is 2 with a remainder of 1. 2 divided by 2 is 1 with a remainder of 0. Keep going. 1 divided by 2 is 0 with a remainder of 1. And you can stop once you get to a 0 here. But if you were to keep going, you're just going to get 0 with a remainder of 0 forever after. Okay, so you go through this whole process until you get down to a quotient of 0 with some final remainder. And now you just write down your remainders in this order. That's 43.
So it goes backwards?
So it goes backwards, and it's depending on how you look at it. All right, so 32 plus 8 is 40, plus 2 is 42, plus 1 is 43. And if you're not sure which way to write it, just follow this out, right? And you've got all these extra zeros. You want those zeros to go on the left because they don't change the value, right? If you wrote this in the other way, then depending on how many zeros you had, your number would be getting bigger and bigger. So that always works, okay, if you're converting a positive number into binary. So just repeatedly divide by 2, write down the remainders, keep going until you divide it down and you get 0. Don't forget your last remainder though, okay? You've got to include that. So have you seen that approach before? So if you wanted to convert negative 43, what do? Convert 43, write it out with the proper number of bits, complement, add 1.
So you'd add 2 zeros to the front?
Yeah, so we'd want 2 zeros in the front. So 43 is that, complement, add 1. That's negative 43. Questions about that?
8 bits is the smallest that we will be working with 2's complement.
No, could be 4 bits, could be 3 bits, could do 2 bits technically. 4 is not uncommon because it saves you from working with really big numbers. 8's pretty typical. But let's, right, so if we have 4-bit 2's complement, and I give you the number 1011, we know it's a negative number because it starts with a 1, right? So this is negative something, yeah,
So 2's complement automatically means sign?
yeah.
Okay.
Yeah, so if we complement this, and we add 1, we get 5. So yes, this is negative 5. Good. So why does 2's complement work? This is a sidebar. You don't really need to know why it works to use it. But why does it work? Does it seem kind of mysterious? It's really just using the idea that x plus negative x should give you 0. And assuming that x is some positive number, to write negative x, we want to write a number such that when we add it to x, we end up with 0. By choosing that as our representation for negative x, we get this fact that arithmetic still works. So suppose I give you this for our number x. How do we find a number that when we add to this, we end up with 0? Well, I'll give you one close answer. If we complement every bit and we add, what are we going to get? We're going to get 1's all across. That's not 0, but it's pretty close. How do we turn this to 0? Just add 1 more, and then everything is going to ripple through to a 0, and we get this extra carry of 1 on the end, which we conveniently ignore. And so the complement of our number plus 1, if we add that to x, we get 0. So that's why we use the complement plus 1 for negative x. All right, so let's talk about fractions. Suppose in binary I write the number 0.1. What's your best guess for what value that might represent? Say again?
1/10.
1/10. So in decimal, it's exactly what it is, right? Why is it 1/10 in decimal?
Because 10.1s fit into 1.
Because 10.1s fit into 1. So in decimal, This is the 10 to the minus first position, the tenths, right? The next digit, that's the hundredths. The next is the thousandths. It's the same weighted positional notation that we use on the left of the decimal point. This is the units, the 10 to the zeros, this is the 10 to the ones, this is the hundreds, 10 to the 2. On the right of the decimal point, this is the tenths, hundredths, thousandths. So if we do the same thing in binary, what weight does this position represent? To the negative first, which is not quite half. So this digit is the halves, and the next digit is the fourths, and the next digit is the eighths and the sixteenths, and so on. So when you write a number in binary, this is the 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on. These are just the negative powers. So with that idea in mind, what number is 0.1 binary representing? I'll put a little subscript 2 here. If that's a binary number, what's the decimal number it corresponds to? Say again? 0.5. So this is how we write 1/2 in binary, 0.1. Okay, how about 0.11? I'll put a subscript on there. If that's a binary number, 0.11, what does that represent in decimal? 0.75. Why? Because it's 1 times 0.5 plus 1 times 0.25. So these powers, this is 1, 2, 4, 8. This is 0.5, 0.25, 0.125, and so on. All right, one more. 101 on the right of the decimal point. Yeah.
What's that 2 below it mean?
This?
Yeah,
It's like writing a 16 to say it's hex or an 8 to say it's octal.
gotcha.
It just means it's binary. So 0.101 binary, how could we find what that is in decimal?
625.
How'd you get that?
0.5 plus 0.125.
Exactly. So it's the same thing we do with integers, and it's really the same thing we've done all our lives when we try to find the value of a number. You take each digit, you multiply by a power of 2 in this case instead of a power of 10. So converting from binary to decimal, again, is taking powers of 2 and adding them up. It just happens to include negative powers of 2, which we're not as familiar with maybe, but it's the same process. And so if you have a number like 101.101, well, this is 5, and this is 0.625. This is 5.625. You don't have to do it in 2 pieces. You could add 2 to the second, plus 2 to the 0, plus 2 to the minus 1, plus 2 to the minus 3, and you'll get 5.625. but sometimes it's easier to just figure out what the left side is and figure out what the right side is. All right, questions on that? So there's one more piece that goes along with that, which again is decimal to binary. So suppose we want to convert 0.375 to binary. Well, we can do the trial and error method. We know it's smaller than 1. We know it's smaller than 0.5. It's bigger than 0.25. We can subtract that, but this is a nightmare, right? Because things just get weird when they're smaller than 1. So there's an algorithm we can use for this, and this will always convert from decimal to binary. And it's almost exactly like the algorithm we just went over. It's a dual to it. So write 0.375, multiply by 2 instead of dividing, and we get 0.75. Okay, take this number, multiply by 2, and you get 1.5. Okay, when we do this, we're only going to carry over the thing on the right of the decimal point. So we're going to take this 0.5, multiply by 2, we get 1.0. Going to take the 0 part, multiply by 2, we're going to get 0.0, and now we're at the point where if we keep doing this, we're just going to keep getting 0.0. And that's where you can stop. And now, we're going to take these pieces to the left of the decimal point. And there's your number in binary. And if we had kept going, we'd get a bunch of zeros over here, and those don't change the value, right? On the right of the decimal point, you can tack zeros on to the right side, doesn't change the value. On the left of the decimal point, you can tack zeros on the left side, and it doesn't change the value. So 0.375 is equal to 0.011 in binary. You want to do one more of these?
Yeah.
So let's convert 0.2 to binary, 20 cents. So multiply by 2, we get 0.4. 0.4 times 2 gives us 0.8. 0.8 times 2 gives us 1.6. What do we multiply on the next line? 0.6 times 2 equals 1.2. 0.2 times 2 equals 0.4. 0.4 times 2 equals 0.8. And if you're not too deeply focused, you're seeing a pattern. right, so let's write our number.
You just go up to 8 times, if it keeps repeating this.
It keeps repeating after like 4 or 5 times. So 0, 0, 1, 1, 0, 0, 1, 1. And at that point, we're probably confident enough to just, keep writing that out, however many bits we're required to write. So 0.02 binary equals 0.00110011. If you were trying to write this as a 16-bit number on the right of the decimal point, it's that thing in binary. But it's not exact, right? Because we really need an extra 0011, 0011 at the end there. And this is potentially interesting because 0.2, that's not a weird number. That's not pi. That's not the square root of 2. It's just 20 cents on a dollar, right? We can't write it exactly in binary. Does that worry anybody? Yeah. Because if you have 20 cents and you want to multiply it by a billion, or by 20 billion, you're not going to get exactly 20 billion times 20 cents. You're not going to get exactly $4 billion. You're going to get slightly more or less depending on which way you round this last bit. And slightly more or less on $20 billion is significant.
Say, isn't that how some people have stolen huge amounts of money from banks?
Yeah, that's the Office Space thing, right? Where they tweak the algorithm and they messed up the decimal point, so. Yeah, so that's an issue. And it's one reason that, especially like in the 60s and even in the 70s, a lot of computers that were working in finance did not use binary, did not use this binary representation to store numbers. They used something called fixed point notation, or binary coded decimal. We'll talk about these another time. Because doing this weighted positional notation, very common numbers don't come out exact. So in some languages, if you take the number 0.1 and you add it to itself 10 times, you don't end up with 1. If you take that sum and subtract from 1, you get something that's slightly positive. And you take the reciprocal and you get some big number. On older calculators, if you took 1 divided by 3, multiplied by 3, and subtracted 1, you didn't get 0. You'd get something with a bunch of zeros and then some stuff on the end. Okay, so that's what's going on with that. All right, so let me give you some homework questions to play with. Well, go ahead and take a break. I'll write these up, and then you can copy them down when you come back. So I'll write them while you take a break. All right, so homework 2. So those first 3 numbers, convert those to 8-bit decimal. For negative 110, convert that using 2's complement. Okay, that's minus 110, that's 110, not 110. And for those next 3, convert those to 8-bit numbers, 8 bits to the right of the decimal point. For those last 2, convert them to 16-bit numbers, so 8 points to the left of the decimal point, 8 points to the right. And then also write those answers in hex. And ignore the decimal point when you do that. Just break the first 4 bits, next 4 bits, period, and then the next 2 bits. So for example, if your answer comes out to be something like that, I would just write that as 2b.37. Right. I just want to see you converting those to hex. It's for my benefit because it's easier to look at a bunch of hex numbers and grade them than to like stare at ones and zeros times 23 assignments times several questions. But if your hex is wrong, I'll look at the binary and see if it's right. All right, so everybody got those?
You say 16-bit binary, that's just like, it's in the top, 6 before and 6 after.
8 before and 8 after, yeah. So this period, we call this a decimal point. But when this pops up between binary bits, technically we shouldn't be calling it a decimal point because these aren't decimal numbers, right? So maybe we should call it something like a binary point. And if we have two hex numbers with a period in between, that would be like a hex point or something. So there's a general term which is radix point. Radix just means what base are we working in. So in binary, that's also radix 2, hex is radix 16, octal is radix 8. So the more general term for this is a radix point, and you'll see that like in texts and stuff. But it's really just a decimal point.
You only want the bottom two in hex?
Yeah. And yeah, so it's 16 bits, just write 4 hex digits with a period in between the first 2 and the second 2. All right, good on the homework? All right, so let's talk about truth tables and logic gates and logic and three-way intersections. So who knows what a truth table is? Who remembers what a truth table is and wants to give a definition of it? Or describe it?
Correct, I think it's a table, it shows possible inputs and then if the output will be true or false.
Shows possible inputs and whether the output is true or false. In school, when we learned to multiply, we learned single-digit multiplication. And in my school, there was a thing on the wall, it was on the door of the code room, right? And it showed a set of numbers across and a set of numbers down, and for each pair of those, you could see what you get when you multiply them. It's a multiplication table. Exactly the same idea as a truth table. It looks different, but it's the same thing. We took all possible combinations of two single-digit numbers, actually went up to 12, and for each of those we showed what this thing called multiplication gives you on those two numbers. So we try to do the same thing for logic. And we could write it like this. This could be an AND. So if you remember, with an AND operation, an AND gives you a 1 if both inputs are 1. So an AND would look like this. And it's basically saying one number is equal to 1 and the other number is also equal to 1. But this only works if we're doing the AND of two things. If we want something more general, like an AND of 3 inputs, this format doesn't work very well. So we usually write a truth table like this. So here's the inputs, and here's the output. And so for a 2-input AND gate, we get something like that. So this is again an AND. And you might write this a little more formally as like X, Y, and then maybe the AND of X and Y. And now it's more clear what's going on. So one of the things that's really nice about working with binary is there's a limited set of possible inputs. To explain multiplication using a multiplication table, we'd need an infinitely big table. Because if you want to multiply 275 times 13,508, you'd have to go over to column 13,578 and come down to the right row, right? But an AND operation only works on ones and zeros. And if it has two inputs, there's only a few possible combinations of those inputs. Could both be 0, could be 0, 1, could be 1, 0, could be 1, 1. So it's possible to enumerate all the possible situations in this finite length table and show exactly what the function does for each of those combinations. So that's all that's going on with these truth tables. And this set of all combinations of inputs also happens to correspond to the way that we count in binary. All right, 0, 0, that's the number 1, that's the number 2, that's the number 3. So usually in a truth table, things are written in that same order. Technically, if we switch these rows around, it's still a valid truth table. But any truth table you look at, almost any truth table you look at, these are going to be written in this order. So if we wanted to do a 3-input AND gate, we might write something like this. And that's exactly what an AND does. It tells you if this first input is a 1 and the second input's a 1 and the third input's a 1. What about an OR? So when is an OR operation give you a 1 for the output? Yeah, if this is 1 or this is 1 or this is 1, then the OR gate gives you a 1. And that's going to be the case almost always. The only exception is that first row where nothing is a 1. So what's the simplest logic operation? Or one of the simplest? A NOT. So a NOT just inverts the input. If you have a 0, the NOT is a 1. If you have a 1, the NOT is a 0. An even simpler operation might be the yup gate, where the output's just whatever the input is. It's a perfectly valid function, but it's not particularly useful. It's really a piece of wire. But you'll encounter those. Well, we can combine a NOT with an and we can get a NOT and. And it's really just saying, let's do an and then complement it. So this gives us a 1, 1, 1, 1, 1, 1, 1, 0. And I like to draw dividing lines every 2 or 4 sets just to keep things lined up. And you know another term for a not and?
Yeah.
That's a NAND. So a NAND is the complement of an and a NOR is the complement of an OR. And it's potentially interesting that a NOR looks like an AND turned upside down. And a NAND looks like an OR turned upside down. That's going to come back in glorious fashion. So we can do logic operations on ones and zeros. And we can have 2 input AND gates, we could have a 3 input AND gate, we could have an 8 input AND gate. And it would have 8 ones and zeros going in. And how many combinations of 8 ones and zeros are there? A lot. More than that, but what's the formula you're using? 2 to the 8th. Right, so 2 to the 8th. 256, who said that? Cool. All right, so 256 rows in that truth table. So that's bigger than I'm gonna draw. I work with some circuits that have 8 inputs, and that's a big truth table. All right, so what is any of this good for? Why do we care about AND gates and NOR gates and truth tables and ones and zeros? What can we do with it? Well, we can use it to design circuits, to do presumably interesting things. So let's make a sample problem. Let's design a combination lock. This is going to be a really cut-rate combination lock. Okay, not the kind you want to use on something valuable. But here's the basic design. We're going to have three inputs. 3 buttons, and each one can be a 0 or a 1. And you're going to set each button to a 0 or 1, and if you set it to exactly the right combination, then the lock opens. And if you set it to the wrong combination, the lock is closed. And we're assuming that whoever's trying to break in isn't smart enough to try all possible combinations. All right, so we have 3 inputs, so let's just call these A, B, and C. So those are our inputs. And here's our output, X. Well, before we do anything more, let's draw a system diagram. So this should always be a part of any circuit that you design, anything that you turn in on a lab that describes a circuit or a system. You should always have a system diagram. So what's the system diagram? It's, as I said last time, it's a 30,000-foot view of your circuit. It skips over the details of how this circuit is going to be put together. What gates you're going to use, what wires and resistors and transistors and magic dust and everything else. It skips all of that. And it looks at this as just what we call a black box. Here's what goes in, and here's what comes out. And the idea of a system diagram is it describes your circuit. It just describes the aspects of your circuit that somebody using this circuit would need to understand. Now, if you're going to the store and you're buying this combination lock, do you care if it uses AND gates or OR gates inside? Probably not. What you care about is, how do I hook this up to my car door? Where do I connect the inputs? Where do I connect the output? And what do the voltages on those inputs and outputs mean? So you would have a key something like this, A, B, C. 1 means button pressed. 0 means not pressed. And X, 1 means unlock, 0 means lock. And assuming you know that a 1 is 5 volts and a 0 is 0 volts, that's all you need to know to use this circuit. So if somebody builds this for you and they give you the circuit and they give you the system diagram, you can hook this up to your car. You get 3 buttons that generate logic 1 or 0. When you press it, it generates a 1. When you release it, it generates a 0. You hook those 3 buttons up to these points. And somewhere on this box, there's points labeled A, B, and C. And there's a point labeled X, and you hook that up to the solenoid that activates the lock or unlock mechanism. And you wire it in such a way that when this outputs a logic 1, it unlocks the door. So it pulls the latch back. And when this outputs a logic 0, the latch engages and the door is locked. So the system diagram, that's somebody who's going to use your circuit, that's what they need to know about it. But by writing a system diagram, we also identify what the inputs are, what the outputs are, and what the logic values for those inputs and outputs mean. So this is the first thing we want to do when we're designing a system. Figure out what the inputs and outputs look like. Put it in a system diagram. The next step is to make a truth table. Well, we know we have 3 inputs, and now we can start to fill in our truth table because we can list all the possibilities for our truth table. And we know the output X should be a 1 or a 0 depending on whether we want the system to lock or unlock for that combination. Okay, well, we're building the circuit, so we've got to figure out what the secret code's going to be. So what should be our secret 3-digit code to unlock this system?
000.
Give me something a little more challenging. Because that's kind of like password baseball, right, or ABC.
101.
101, okay, I'll accept that one. So, password equals 101. Don't tell anyone, because they'll break into my car. Okay, with that information, we can fill in this truth table. Because we know that if the input is 000, that's the wrong password, the door should be locked, and when we want the door to lock, X should be a 0. So this should be a 0. And 001, that's also the wrong password, door should be locked, that should be a 0. And in fact, this is the case until we get down to 101, which is the password. If we put in the right password, the door should unlock, and X equals 1 means unlock. So in this case, we want X to be a 1. And in these cases, we want it to be a 0. So there's a truth table for this combination lock. And that's generally the second step of this design process. First make a system diagram, then construct a truth table. And I think, is that as far as you need to go for experiment 6? Input and output variables, sketch the intersection, identify the variables, develop a truth table. Okay, so that gets you through experiment 6. So that includes a picture of your intersection, a system diagram, and a truth table. Well, you don't need to do this for lab 1, but eventually we're going to want to build a circuit that will implement this truth table. So, yes?
I guess a quick question about, you said this was enough to do lab 6. But
Experiment 6.
Sorry, experiment
Yeah.
6, my bad. But so in this case, what you've shown us is there's 2 possible outputs.
Mm-hmm.
But then for experiment 6, is there 3 possible outputs it needs to be because of the green?
Actually 6, because you have a red and green light on each lane. So we make a truth table for each output.
Oh, did you make more?
Yeah.
Okay.
And if you like, you can actually list multiple outputs in a single truth table because you always have the same set of inputs.
Okay.
But really what you're doing is you're creating 6 truth tables, even if you combine them into one. Thanks. It's good clarification. All right, I want to simplify this problem for a moment. We'll work on a simpler problem. and then we'll come back to the real one. Suppose we had picked the password to be 111. So this is what the truth table would have looked like, right? Door is locked in all cases except when the inputs are 111. Okay, so we're given this task. Someone's paying us $500 million to develop a circuit for this truth table. So we're anxious to get to work on this. So we want X to be equal to some logical function combining A, B, and C. Could have NAND gates and NOTs and ORs and XORs and flip-flops and all kinds of things we're going to learn. Logically looking at this, is there a way that we could describe X in terms of A, B, and C that we've already talked about?
A and B and C.
A and B and C. Let me write it like this. So if we luck out and we're asked to write a truth table like this, it's easy. It's one logic operation. We want the output to be 1 when A is 1 and B is 1 and C is 1. Okay, we're not always that lucky. And in this case, to get our $500 million, we're going to have to do some more work. Because we want our output to be 1 when A is 1 and B is 0 and C is 1. And we don't have an AND gate that tells us when the middle input is a 0, right? We have an AND gate that tells us if all the inputs are 1, and we have an OR gate that tells us if any of the inputs are 1. But we're looking for something kind of in between those. We want to know that A and C are 1, but we want to know that B is 0. So here's what we can do. We can always change the problem. Instead of saying I want B to be 0, I'm going to say I want not B to be 1. Hey, we just made our life easy. Because now we want X to be 1 when this is 1, and this is 1, and this is 1. And that we can do like that. So if we can take A and not B and C and AND those together, that's the X we're looking for. Okay, once you've wrapped your brain around this, you got the first 2 weeks of the course. Okay, we're going to do lots of variations on this, but this is really all that's going on. We're using the fact that we have a gate, an AND operation, that can tell us if 3 things going into it are 1. And we're using that to find out if our inputs are actually 1, 0, 1. How do we do that? By first taking that middle bit and turning it into its complement by running it through a NOT operation. So A ANDed with not B ANDed with C. That gives us our value for X. Okay, if we don't believe that, we can verify it. So here's A, B, and C. Let's write down what not B is. It's just the complement of B, so it's 1, 1, 0, 0, 1, 1, 0, 0. And now let's write down the AND of A, not B, and C. And this means you want to take this column and these two columns and AND them together. So 0, 0, 1 is a 0, 0, 1, 1 is a 0, 0, 0, 0 is definitely a 0, 0, 1, 0 is a 0, 1, 0, 1 is a 0, 1, 1, 1, that's a 1, 1, 0, 0 is a 0, and 1, 1, 0 is a 0. And did we succeed? Absolutely. It's exactly what we were after. All right, questions on any of this stuff? So let's introduce some symbology so we don't have to keep writing out parentheses and things like that. So we have some shorthand that we can use to talk about these logic operations. So when we talk about ANDing A and B, sometimes we use the term product. This is the product of A and B. And we can write this as A and B with a period in between them. And sometimes we skip the period just like with multiplication and we just write AB. And if we're drawing a circuit diagram, we have a piece of circuitry that looks like this. And I usually put the period in the middle of that diagram, that symbol. And so this is a symbol for an AND gate, a piece of circuitry that takes two inputs and ANDs them and produces an output. So when we OR, that's sometimes called a sum, and we write it with a plus sign. And it's not addition, right? It's just a different symbol. And our circuit diagram for that kind of looks like an AND gate, but it's got this curve on the beginning. And to make it clear that this is curved, I put a plus in the middle. So it's absolutely clear this is an OR operation. So a not AND, that's a NAND. And it's an AB with a bar on top. I should have done a not first. So a not of A, and that can be called a complement or an inverse. And we just write A with a bar on top. But when you're typing, it's hard to put a bar on top of a character, so sometimes you see this as A with a little single quote before or after it. I'll avoid that. I'll put bars in. And the symbol for that is a triangle with a circle in the middle. Circle at the end. So that's called an inverter. So a not AND, which is a NAND, that's AB with a bar on top. It means do the AND and then negate it. And the symbol for that is an AND gate with a circle on the end. So these circles generally mean negation, inverse, complement. And a not OR, that's our NOR. And it's A plus B with a bar on top. And you can guess what the symbol's gonna be. Just an OR gate with a circle on the output. So you've seen these in 120, probably. Just kind of review here. But we'll stick to this shortcut notation and these symbols when we're writing equations or drawing circuits. So if you're not sure what they mean, you can come back and refer to this. All right, so back to our combination lock. We're still trying to get our $500 million. So X is the AND of A, not B and C. So a better way to write that might be like this. A ANDed with B bar, ANDed with C. Well, can we design a circuit to create this value X based on A, B, and C? Absolutely. And it's really not too hard. We need an AND gate. The output's going to be X. One input is going to be A. Another input is going to be C. And this input is going to come from an inverter, which is going to come from B. And there's your circuit. So if and only if A is 1, B is 0, and C is 1, our output's going to be a 1. Any other combination, the output will be 0. So this is usually our third step, sketching a circuit diagram. All right, well, our customer is a little fickle because we bring them our beautiful circuit and they say, oh, actually, I wanted something else. They want to be able to give a combination to a friend so that their friend can also unlock this system. But they don't want to give them the password 101 because that's the password this person uses for everything. So they want to give their friend a second password that will also unlock this. So what should we use for a second password? You want to do your 3 zeros? 010, okay. So they say, this is what I really want. I want the system to unlock with this password, but also with this password. Give me a circuit for that, and then I'll pay you. Okay, so this line here is saying the same thing. We want X equals 1 when A equals 1 and B equals 0 and C equals 1, and we modified this to say B bar equals 1. So we phrase this in the language of an AND gate. X should be 1 when A is 1 and B bar is 1 and C is 1. But we have this new additional requirement that x should be 1 when a equals 0 and b equals 1 and c equals 0. And we can rephrase that as a bar equals 1, c bar equals 1. Okay, if this was the only output that was going to be 1 in our circuit, we could just use a different AND gate setup. We could take a bar, ANDed with b, ANDed with c bar, and take the output and call that x. And if this is the only one output, we can do a, ANDed with b bar, ANDed with c. So we have two goals here. This will produce a 1 exactly when this input matches. And this will produce a 1 when exactly this pattern matches our input. To satisfy this customer, they want a 1 when either of these conditions is true. When this is true or when this is true. So how can I write that using our, right? That's all there is to it. So if I say x equals this or that, I've described this truth table perfectly. Because x should be 1 when this condition is satisfied, which is right here, or when this condition is satisfied, which is this row right here. And any other cases, x is going to be 0. And this is a process we can easily generalize. In fact, it's so easy to generalize, we can write a program that will produce these equations for us from a truth table. So there's an algorithm we can follow for writing these things down, but this is the idea, okay? And I want to make sure you understand the idea. The algorithm is just something we're going to learn and we're going to do. But it's important to understand what's going into that algorithm, right? Everywhere that we have a 1 in our output variable, we have some combination of the inputs that we AND together. And then we take all those combinations and we OR them, and that'll give us an output that's 1 in any of those situations. So questions on that? So let's generalize this. And let me put something intermediate in here. Up here, when we were in this third row, 0, 1, 0, we thought about this and we said we want A to be 0, which means A bar should be 1, B should be 1, and C bar should be 1. And so we came up with this term, A bar, B, C bar, that kind of corresponded to this third row. I want to write down these terms for each of the 8 rows, so that in the future we don't have to go through this mental step. So if we want a 1 in this last row, we know that's just A, B, C. If we want a 1 in the 6th row, we know that we want A to be 1 and B to be 1, but we want C to be a 0, so C bar is a 1. And here, this was the one we started with, this was A, B bar, C. What about this 1, 0, 0? What's the AND expression that corresponds to this set of inputs? All right. A, B bar, C bar. All right, someone else, what's 0, 1, 1? Did you have a question first? Okay. So what's 0, 1, 1?
A naught BC.
A naught BC, good. 0, 1, 0, we already did. Someone else, 0, 0, 1?
I bar, B bar, C.
A bar, B bar, C, and the first one, 0, 0, 0. Well, it's not nothing. Yeah. We want A bar to be 1, and B bar to be 1, and C bar to be 1. So these things are called minterms. Yes?
Is it outlandish to connect the bars?
Yes. Don't connect the bars. Don't cross the beams. Really important. If you connect the bars, you get something very different. And so if you're in doubt, sometimes I'll put parentheses around these just to keep them separate. Thanks for asking. I meant to mention that. I forgot.
It's like min term?
Min terms, like minimum. Yeah. Okay, knowing these min terms is useful because suppose we have a truth table like this. We want X to have those zeros and ones. If we know these min terms or we have a list of them somewhere, we can immediately write everywhere that we have a 1, write down the corresponding min term. And just OR them all together. Right, and this just came from here. And this came from here. And there. And there. And now we don't really have to think anymore. Right, we got a truth table for X and we want to write an equation for it. We just take the min terms everywhere that we have a 1 for X and we OR them together. Does that make sense? Now you don't need to memorize these min terms, which is a good thing because they all kind of look the same. There's an algorithm we can use to find out what the corresponding min term is for any set of inputs. Anybody see what the algorithm might be? So here we've got 1, 1, 1, and here we wrote A, B, C. Here was 1, 1, 0, and we wrote A, B, C bar.
Don't you just put the bar over whichever one's 0?
Yes. So whatever the values of A, B, and C are here, if there's a 0, put a bar over the corresponding input name. If there's a 1, just write down the input name itself. So A, B bar, C bar, or A bar, B bar, C. And so if we have 15 input variables, we can do the same thing. We just write down those variables, and anywhere that the input is a 1, put a bar over that variable. All right, questions? So let's start the truth table for this three-way intersection. So you're going to want a system diagram. And its inputs are going to be these sensors that tell you whether there's a car on each lane. I'm just gonna call these W, S, and E. And then we're gonna have 6 outputs, which I'm going to call west green, west red, south green, south red, east green, and east red. And I'm going to say for the sensors, 1 means there's a car present, 0 means there's no car present. Does it have to be like that? No, we could do this with 0 means there's a car, 1 means there's no car. In the last lab, you'll actually use that particular meaning. But more often we think of 1 as like the action option. So there's a car present, that's a 1. Okay, these outputs, west green, west red, south green, south red, east green, east red. 1 equals the light is on, 0 equals the light is off. Again, it could be the other way around. But you've got to decide what 1s and 0s mean, and you've got to indicate that. So let's just make 1 column of our truth table. Let's just do south green. Okay, so the right-of-way rules that we're using on this intersection is the car on the right gets precedence. So if there's a car on the right, if there's a car on the east, nobody else gets to go. If there's no car on the east, but there's a car on the south, that car gets to go. And if there's no car on the east or south and there's a car on the west, the car on the west gets to go. If there's no cars anywhere, we haven't said what to do. You could make all the lights red, you could pick 1 light to be green, okay, but you can never have more than 1 light green. All right, so with that understanding of how these lights should be turned on and off, we have enough information to fill in this truth table. So we're trying to indicate whether the south light that's green should be lit or not lit. So let's look at this first row. So there's no car on the west, no car on the south, no car on the east. What do we want to do in that situation?
Red.
It's not specified. Let's make everything red, okay? So south green will be off. You might give west a break, but it's not going to affect south. Okay, second situation, there's a car on the east. Should south green be on or off? Should be off. Third situation, there's no car on the east, but there's a car on the south. So that should be on. Fourth situation, there's a car on the east and a car on the south. So south should be off. All right, fifth row, there's a car on the west, no other cars anywhere else. South should not be green in that case because west is going to be green. East and west, no car on the south. South's not in the mix at all. Car on the south and a car on the west, but nothing on the east. That should be on. We're going to give south priority. And now there's cars on all 3 lanes. East gets precedence, so south green should be 0. You're done. There's your truth table for south green. So do that 5 more times for your other 5 lights, and that's experiment 6.
Why can't you simplify it to 0 being red and 1 being green?
You can do that. And if you want to do that, you're welcome to do that.
Okay.
The only detail is if you do that, right, your system diagram is going to have 3 outputs, and you got to be really clear when you label these. 1 means light is red or green, 0 means light is red or whatever. Right, but that's a perfectly fine way to do it. In the last version of this, that won't work because we're also going to have yellow lights.
Yeah.
But for getting to there, yeah, that works great. All right, so questions about that? All right, so that should be all you need for making a truth table for that experiment. Just make sure you show your intersection, you describe these, and do more than this, right? Put a few words in, say west, south, and east are sensors. One means a car is present, 0 means a car is not present. These are lights that control, whether the car can go. 1 is on, 0 is off, or 1 is green, 0 is red. All right, one more thing I'll mention here, we'll come back to this more next week, but since we've already got this up, regardless of what the truth table is that we're implementing, if we're implementing a truth table with 3 inputs, we're always going to have these same min terms, right? A bar, B bar, C bar, A bar, B bar, C, A bar, B, C bar, and so on, right? We have a shorthand for writing this, because writing out A bar, B, C bar, or A, B bar, C bar takes a lot of writing, right? And these things never change, right? We might have A bar, B bar, C or something, but it's always going to be the same 8 terms, just in different combinations. So we actually have a shorthand for each of these, which is just a little m followed by a subscript. And the understanding is, since our inputs are A, B, C, M5 means A, B bar, C. And if we have that understanding, we could actually have said X equals M2 or M4 or M5 or M7.
Instead of M, can you have like SG?
Say again?
How we had SG, like south green.
Mm-hmm.
Instead of have M, just have SG.
For here?
Well, not for here, but for the lights and stuff.
So it's technically a lowercase m with a subscripted number to represent min terms.
Okay.
It's just a standardized,
Okay.
right? So M0 means A bar, B bar, C bar. So we'll work with these next week, but it's going to let us use a shorthand to represent big long equations like this using just these min terms. All right, so catch me in lab or office if you have questions on the lab or on the current homework or on the subject matter. Otherwise, I'll see you Tuesday. We'll start designing circuits to implement some of these equations.